Welcome to Educator.com. In today's lesson, we're going to be doing inverse variation. Recall from an earlier lesson, we discussed the concept of direct variation. In direct variation, the equation described a relationship between two variables. Inverse variation also describes a relationship between two variables, although it is a different relationship. In inverse variation, you have a relationship between two variables, x and y, in which the product xy is equal to some non-zero constant k. So writing that out, that gives you the equation x, y equals k. So k is known as the constant of variation. When we're discussing inverse variation, we sometimes say that y varies inversely as x. And you can see that you can manipulate this equation to end up with y equals k over x. So in inverse variation, we say that y varies inversely as x. The relationship between these two is such that when x changes, y will change in such a way that k remains constant. And we can also discuss this by saying that the relationship is such that y is proportional to the reciprocal of x. There are actually many real-world examples of inverse variation. For example, we could say that the time it takes to get somewhere varies inversely with one's speed. So if you run faster or drive faster, your speed increases and the time it takes to get there decreases. So this is inverse variation. And just to make sure you're clear on the difference between inverse variation and direct variation, in direct variation, we have the relationship y equals k times x, which would then, it could also be rewritten such that y over x equals k. So you see in this inverse variation situation, the product of x and y equal k. In direct variation, the quotient y divided by x equals k. So both of these describe relationships between two variables. However, it's a much different relationship. Okay, just as we graph direct variation, we can also graph inverse variation. And if we use the form xy equals k, we can form a graph by finding values for x and y. And as I mentioned, there's a lot of real-world applications to inverse variation, and some of these applications require that x or y assume only positive values. For example, when I just talked about the relationship between the time it takes to get somewhere and speed, you know that time cannot be negative. So we're not going to say that it took negative 5 minutes to get somewhere, and the same with speed. So in those cases, we would have positive numbers for x and y. And that's going to affect what we end up with for the graph. Let's go ahead and take an example here and see what this looks like. So if k equals 10, if the constant of variation is 10, then the equation for inverse variation is going to look like this. The product of x and y equals 10. So let's go ahead and graph that out by assigning some values to x and determining what the corresponding values for y will be. Okay, so if x is 1, well, we need the product of x and y to equal 10, so then y must be 10. If x is 2, so then I have 2 times y equals 10. Simply dividing both sides by 2, I'm going to end up with 5. So in order to find y, I'm just going to find 10 divided by x. Okay, Next, if I let x be 5, you can see that y is going to be 2. And if x is 10, y will be 1. So right now I'm just working with some positive values, but we'll do some negative values in a minute because I'm not putting that restriction on this equation stating that, x or y needs to be a positive or negative value. We're just going to let it be either. So graphing. First, when x is 1, right about there, y is 10. When x is 2, y is 5. When x is 5, y is 2. And when x is 10, y is 1. You could even take some more extreme values to see what's going to happen. For example, if x is 20, you can see that y is going to be 1/2. So as x becomes larger, this graph approaches the y-axis. The same thing's going to occur up here. For example, if I say, let's let x equal 1/10. Well, if I have 1/10 down here for x, I'm going to end up with a value of y equals 100. So as x gets smaller, we see that this graph is approaching the y-axis. So in a graph for inverse variation, what you end up with is a curve called a hyperbola, in which the curve approaches the x-axis and it approaches the y-axis, but it never actually crosses them. So this is called a hyperbola. And what we have here is just one branch. So there are two branches or arms. Sometimes they're called arms. This is one branch or one arm of the hyperbola here in the first quadrant. Now, I'm going to go ahead and take some negative values for x to determine what the graph of the other branch looks like. Beginning with x is -1. Well, if x is -1, you can see that since k is a positive value, y is going to be a negative value, and it's actually going to be -10. If x is -2, y will be -5. If x is -5, y is going to be, let's see, so just working this one out. Just to show you how this is going to work. If x is -5, then we're going to solve for y, and y is going to have to be -2. And so I've worked a lot of these out in advance, but just to show you how this is done. If x is -10, y is -1. And you can see it's just the corresponding negative values compared to what we have over here. So I'm going to go ahead and graph these. Okay, so when x is -1, y is down here at -10. X is -2, y is -5. When x is -5, y is -2. When x is -10, y is -1. And you can see the same shape of a hyperbola, where we have a curve that approaches but never reaches the x-axis or the y-axis. So we have the second branch of the hyperbola here in the fourth quadrant. Now, the value of k tells you whether the branches are going to be in the first and fourth or in the second and third. When k is greater than 0, the branches are in quadrants 1 and 3. Excuse me, this is actually the third quadrant. 1 and 3. When k is a negative number, when k is less than 0, the branches of the hyperbola are going to be in quadrants 2 and 4. Quadrants 2 and 4. So when you go to graph an inverse variation, you already know that the general shape of the graph is going to be a hyperbola. And if any values for x and y are allowable, then you're going to have two branches. If k is a positive number, the branches will be in quadrants 1 and 3. If k is a negative number, then the branches are going to be in quadrants 2 and 4. Okay, so let's look a little more deeply into what we can do with inverse variation. Suppose that you have two sets of points, x1, y1, and x2, y2, that both satisfy the inverse variation, the product of xy equals k. So if you think about this, if a set of points equals, their product equals k, then x1 times y1 must equal a certain value. We don't know what that value is, we're just calling it k. A second set of points would also satisfy that value of k. So the product of x2 times y2 is going to equal the same constant. That means that the product of this and the product of this equal the same number. They therefore equal each other. So what this tells us is that x1, y1 equals x2, y2. And this is called the product rule. You can manipulate this equation by dividing both sides by x2 and y1 to end up with this form of the equation. And what's helpful about this, the application, is that if you know 3 points, you can use this rule to find the fourth point. And that's exactly what we're going to do right now in the examples, in some of the examples. Okay, in the first example, we're asked to do some graphing, and it says graph the inverse variation, the product of x and y equals 24. So x times y equals 24. Assume that x must always be positive. So here we have xy equals k. And I know that my graph is going to be a hyperbola that is going to have, it could have branches in quadrants 1 and 3. However, I'm given the restriction that x must always be positive. So if x is always going to be positive and 24 is positive, y must end up being positive. So I've already got an idea in my mind that I'm going to have some kind of hyperbola, and it's going to be up in this first quadrant only. So to graph, you go ahead and pick some values for x, and then determine the corresponding value of y. So if I'm solving, what I need to do is solve for y. So y is going to equal 24 divided by x. Therefore, when x is 1, y is 24. When x is 2, y is 12. When x is 3, 24 divided by 3, y is 8. When x is 4, y is 6. I'm going to skip 5 because that doesn't divide. 24 cannot be divided evenly by 5. 5 is not a factor of 24, and I have plenty of points, so I don't actually need to get into that messy point. 24 divided by 6 is 4. 24 divided by 12 is 2. So that gives me plenty of points to go about graphing this. Okay, this is going to be, I have plenty of points, and this first point is, I have the general idea that it's going to be at 1, and 24 is way up here somewhere. So let's go to the second point. When x is 2, y is 12. It's going to be right about there, 12. When x is 3, y is 8. So x is 3, y is 8. When x is 4, y is 6. When x is 6, y is 4. And you can already see it starting to curve. When x is 12, right about there, y is 2. And just as we discussed, the graph of this is a hyperbola, that the curve is such that the graph of this will approach. So it's going to approach the x-axis, it's going to approach the y-axis, but it's not actually going to reach either of those axes. So this is the graph of the inverse variation described by xy equals 24. It's because x is always positive and we're given a k that is positive, we're just going to have one branch of the hyperbola that's located in the first quadrant. In my second example, I'm again asked to graph an inverse variation. And again, this is in the form xy equals k, but this time I have a k that is less than 0. And that tells me that the branches are actually going to be in quadrants 2 and 4. And there's no restriction put on what x can be or what y can be, so I'm going to use both negative and positive values for x to make sure that I get both branches of the graph. So let's pick some values. And solving for y here, I'm going to get y equals x, or excuse me, y equals negative 12 divided by x. Therefore, when x is negative 1, y is 12. When x is negative 2, y is 6. And you can always check this, seeing that, negative 2 times 6 is negative 12, which is what the inverse variation is stating. When x is negative 3, y is 4. When x is negative 4, y is 3. I'm going to go for some positive values. And there's not going to be a 0 because if I made this 0, I would just get 0 over here, and k cannot equal 0. So I'm going to go on and choose some positive values. When x is 1, then k is going to have to become negative. It's negative 12. If I plug in x is 2, y is negative 6. X is 3, when y is negative 4. And when x is 4, y is negative 3. Okay, so graphing this. When x is negative 1, right here, about here, y is 12, so up here. When x is negative 2, y is 6. I'm moving this point over just a little bit so it's closer to negative 1. Okay, when x is negative 2, y is 6. When x is negative 3, y is 4. You can already see it starting to curve. So that gives me the idea that this is going to curve. And I can do actually some more points. I see that I need a few more points to actually get the other arm of this. So let's go ahead and graph out negative 6. When x is negative 6, y is going to be 2. So I needed another point here to give a more complete graph. Okay, I have one branch of the hyperbola, one arm. The second arm is going to be when the values of x are positive, and that's going to give me negative values for y. Therefore, when x is 1, y is negative 12. When x is 2, y is negative 6. When x is 3, y is negative 4. Again, I'm going to want to go a little farther. And as you're graphing, you sometimes graph and you see that in order to get a complete graph, you need a few more points, or maybe 1 or 2 more points. So when x is 6, y is going to be negative 2. So I'm going to go ahead and graph that out. When x is 6, y is negative 2. I can even do a couple more. When x is 12, y is negative 1. So that helps me finish it out. Okay, so I am going to have a graph such that I have a hyperbola that is approaching, but it's not quite going to touch. It's never going to actually reach this axis. It's going to approach it, but never reach the x and y axes. And it's a hyperbola with 2 branches in quadrants 2 and 4. In this example, we're told to assume that y varies inversely as x. So that tells me that xy equals k. And I'm given an x value equals 27 when y equals 3, and asked to find x when y equals -9. So what I've been given is an x1 value, a y1 value. I'm asked what x2 is when y2 is a given value. And if you recall from the product rule, x1, y1 equals x2, y2. And this follows from the fact that the product of x1, y1 is equal to the constant variation k, and x2, y2, the product of those two, is also equal to k. Therefore, these two products must be equal. Knowing that, I can go ahead and take my 2 points, and writing these out so that it's clear, my x1, y1 are 27 and 3. My x2, y2, x2 is unknown, and y2 is -9. So I'm being asked to solve for x2. So I'm going to go ahead and plug in these values into this equation. So that's going to give me 27 x1, y1 is 3, equals x2, which is unknown, times -9. So all I need to do now is solve for x2. I'm going to divide both sides by -9. So it's going to give me 27 times 3 divided by -9 equals x2. Well, I can go ahead and cancel out a 1 here, and that gives me a 3. So I have 27 divided by -3. x2 equals -9. And I determine this using the product rule, which tells me that the product of one set of points is equal to the product of the second set of points. So if I have 3 of the 4 points, I can find the 4th point. Assume that y varies inversely as x. If x equals 12 when y equals 4, find y when x equals -1/2. Again, I'm given 3 points, and I'm asked to find the 4th, so I'm going to use the product rule. x1, y1 equals x2, y2, which follows from the fact that this product and this product are both equal to k. Therefore, they're equal to the same value, so they are equal to each other. Now, I have an x1 right here. That's 12. I'm going to write out my points. 12, y is 4, so 12 and 4. And my second set of points are y1, y2, which is unknown, and x2, which is -1/2. So my second set of points is -1/2 y2. I'm going to go ahead and write plug these values in for the different variables. So I have x1 is 12 times y1, which is 4, equals -1/2 times y2. In order to solve this, I need to multiply both sides by -2. So it's going to give me -2 times 12 times 4 equals -2 times -1/2 times y2 to isolate the y over here. This is going to cancel out. So I'm just going to be left with 1 times y2, or y2. -2 times 12 is -24, times 4 is -96. So y2 is equal to -96. And I was able to determine that using the product rule, which describes this relationship between two sets of points in an inverse variation. So today on Educator.com, we discussed inverse variation, did some graphing, and learned how the product rule can help you to find a missing point given 3 other points in an inverse variation. See you again soon.